Thank you. I'm glad to be here, not only for the 40th anniversary of these conferences, but for me, it's also the 4th anniversary of my first paper that was in the Atlanta conference, the first ICRO. So today, I'm going to talk about redundancy in multi-arm surgical robots, not technical aspects because of time, but some comments on a trade-off for its usability and efficiency. I'm using the two hats at the university and the company and worry about these aspects. From the first surgical robot, first commercial surgical robot, that was the first Da Vinci with 3 arms, one for holding the laparoscope and the other 2 for the surgical instruments. There have come many other robots in the market or close to the market, some of them having only 1 arm, like this in orthopedics. It went out. Oh, what's this? Okay, the contact. Once some of them on only 1 arm, like for radiotherapy or for orthopedics, but in laparoscopic, for example, we need more arms, and the standard has become 4 arms. Here, inspired by this first robot, which have the heritage of industrial robots, basically, what we can see is that in industry in general, we use robots with 5 degrees of freedom. In general, the tool has a rotational axis, so 5 or 6 axes is the common thing for positioning and orientation. And surgical robots, we have to position, but we need to maneuver inside the body, and we need more 3 end joints for positioning, and even more for positioning and orienting the instruments. Coming ahead in industry, we have the general standard. We have 1 task. We have 1 robot for the task. If we have many tasks, in general, there are many robots, each one in its place, with a specific assignment of a task. In surgical robots, we may have these different situations. 1 robot, 1 task, like here in orthopedics, but on other tasks, we need more than 1 arm. And many arms working together in a reduced working space. That means that we need redundancy to avoid collisions. And this can be implemented in the different arms of the robot, or with the initial positioning of the robot. Placing the robot in different places can give the different working space. In laparoscopic surgery, we have still other constraints. That is, the instrument is entering through an incision in the abdomen. So we have to hold the instrument that is pivoting around this point. And for that, we need redundancy. And this redundancy means that we have to see how to manage at every moment in order to cooperate all the robots together. What we have seen is that as robots have been going on this field, there have been two basic trends. One is having 4 robots, 1 arm each, or having one unique robot with 4 arms. And apart from that, we have seen that there are robots with high redundancy to avoid these collisions, and others with low redundancy. And what I want to show or discuss a little bit is some characteristics of all of them. So these are examples of these different robots we have: the Hugo robot, the CMR, the Da Vinci, and the track of Rab Surgical, our robot. And for that, let's see some aspects. With high redundancy, of course, we have robots with high complexity, while low redundancy implies less or lighter robots. If we see the first row, robots have a large footprint because they are different modules around the patient, and the others, the second row, has the forearms more, let's say, more concentrated, so the minor footprint on the floor. This also implies different things. For the first column, we see that the trocar, so the incision point, is fixed. And because of this high number of degrees of freedom, they can fix this point. And so at every moment, it is very exactly computed the position of the tip of the instrument where the robot is operating with, while the others have floating trocar. That has implications. In the first case, as the robot is fixed in this position, or the instrument is fixed in this position, and the abdomen of the patient can move a little by breathing or other movements, they can cause small skin wounds like hematomas. But also, what we have to consider is that thanks to this positioning of the instrument with the degrees of freedom at the last degrees of freedom, they can have high stability. On the other side, these other lighter robots have minor skin wounds because the robot follows the potential movements, and this implies a little less instrument stability, but as has been shown, is good enough for the interventions. This, as a consequence, what we can consider about usability is that in this first, the arms accessibility can access the operating area and maneuver without moving the robot, and this is good, but the magnitude of the robot, the size of the robot due to this high number of degrees of freedom makes difficult for auxiliary staff, for auxiliary surgeons move around the patient, and the compatibility of the different arms at the initial, at the starting of the intervention is complex because there are many degrees of freedom. 1 degree of freedom can be automatized. We can fix some parameters to deal with the redundancy, even a function, depending on the distance, depending on the movement of the other arms, you can control how to manage the redundancy. But when there are more degrees of freedom, the computation explodes, and all this positioning is done manually with an effort from the specialist. In this other side, we see this accessibility around the robot is easier because the space, they give some space for humans. There is compatibility between the arms by adjusting easily the robot, but the accessibility to the different area implies that initially we have to position the robot in the right place. The second robot, or the second kind of robots, also has the same characteristics due to this high number of degrees of freedom and its size, while this other is light and allows this easier, let's say, accessibility and going inside through the patient and arms accessibility. But this depends on the physical robot architecture. This has been the challenge to deal with these aspects. So what we can see here is how the setup of the robot, that we see that is very quickly. We don't need to manage all the links of the robot because we have small redundancy, one in some arms and not on the other. So the other thing is all the arms have to be redundant or only some of them. And with this goal, thinking on this usability and this more simple equipment, the challenge is to move from robots that are useful and very appreciated for surgeons and patients in the operating room, but can only be affordable for big and complex hospitals, while we pretend to reach medium hospitals in which the number of surgeries per year do not justify having one such system. And this is the considerations I wanted to put on the table. Thank you very much for your attention.
Yep. Yep. Thank you, Alicia. Perfect, on time. Questions for our speaker? While the next speaker.
Thank you for your talk, Alicia. I think one point is a touch for surgery. What about this kind if you have minimal invasive interventions, you have contact, you must identify cells and so on. And this is usually haptic and touch. What about that?
Haptics is the other challenges. Here I was talking about redundancy, but of course, haptic is the effort that all of the researchers of all the robots are trying to introduce. The problem in general is how to detect the force at the tip of the instrument due to incompatibilities, miniaturization, and other parameters. And there are different ways of measuring force or estimating approximated force and give some feedback. So we get some information about, there are studies about having impedance to detect contacts and give some of the feedback, but because of course interoperation, one of the main limitations if we don't have this haptic feedback is that we don't feel what happened on the other side. So there are steps advancing in these directions. In general, there are not feedback, but it is entering. We have a little information of detecting contacts more than precise measure of force.
Alessandro.
Hi, Alicia. Do you think that the current methods about handling redundancy, like task priorities, stack of tasks, task augmentation, are enough for solving the problem in medical robotics, or do you need some new technique that are not addressed? I mean.
Well, the problem is the number. So we have to advance on all these classes to see how to manage the problematics and the high computation that it implies. That is what motivated us to reduce or try to see how to reduce the maximum the redundancy that is enough for that. But of course, there have to be, as we increase these degrees of freedom, or work hard on managing all this. But because computation increases and we have to see the ways to solve it in real time, quite efficient enough.
Okay, great. Thank you very much, Alicia. Yeah, let's thank the speaker. That's good. Yeah, thank you. Very nice. Very nice.
Yeah.
Yeah.